Hello everyone, and welcome to the MATLAB and Simulink Robotics Arena. Today's video, we have a special guest, Kurt Talke from the University of California, San Diego, and the two of us are going to talk about programming BeagleBone Blue with Simulink. So thanks for being here, Kurt.
Thank you.
Just for the viewers really quickly, would you like to say a few things about your association with MATLAB and Simulink and what we'll talk about today?
Yeah, so I'm a PhD student at University of California, San Diego. Been working with MATLAB, the BeagleBone Blue, and Simulink for the last 3 years or so. And I was one of the prime developers in porting software library that works with C on the BeagleBone Blue into Simulink so that we can do graphics-based controls, which is sort of native to Simulink and what it's good for.
Thank you for that. So we talk about MATLAB and Simulink a lot in this series, not so much about BeagleBone Blue. So we'll just do a quick agenda here. So again, the first question might be for the viewers, what is BeagleBone Blue? Secondly, how do we connect that to Simulink? And then we're going to go into a case study with this eduMIP robotics kit, which you will be able to see shortly. So let's start with BeagleBone Blue. I know, Kurt, you've been working with this for a while, so why don't you tell us a little bit about this hardware?
So BeagleBone Blue initially started as a backpack or cape for the BeagleBone Black. The BeagleBone Black and Blue are based off the same architecture. They're Linux-based computer, low cost. But the idea with the BeagleBone Blue specifically is that we've taken all the hardware that's on the backpack or cape and integrated it directly onto the BeagleBone Blue. So now it's one board specifically built for robotics that has an IMU, it has a DSM-2 radio if you want to do some UAV flight robotics. All the IOs you would want, UR, SPI, I2C. What's really nice, it has 4 motor drivers, so H bridges to run 4 motors, and it has 4 encoder counters. And what's really great about it is the software support for it. One of my colleagues has spent a number of years developing this software library that's fully sussed out and works well with all the low-level hardware. So it's a great learning environment for not only Linux-based computers, but also for touching hardware and robotics. The software library has C functions that handle all the drivers. So there's a function that says output to motor. There's a function that says get encoder. So really all you do is plug it in electrically, and then in your whatever code you want to write, just say, hey, get encoder, and it does all the communication for you and gets the
Right.
values out.
Yeah, so that's kind of where we get to the Simulink portion, right? So these same robotics cape functions or this library that we're talking about, right? You can use it as regular code, and with the Simulink coder support package, these now get wrapped into Simulink blocks. And for those of you watching this series, hopefully Simulink's a little bit familiar, where now everything that involved reading a sensor or writing a command to an actuator can be placed in these graphical blocks, and then you would fill things in the middle. And there's kind of two workflows that you can take with Simulink to do all of this, right? The first one is to basically write your model in Simulink, hit the build button, and then get some standalone C code that makes it right onto the hardware. But the other thing, which we'll also show you in the demonstration, is this notion of external mode, which is not just generating the C code from your graphical model, but actually having this communication layer where you can still interact with the Simulink diagram. So you can change parameters, you can view the results on a scope or a display while the actual code is running on the BeagleBone Blue.
One thing I want to say that's great about Simulink is that it's graphical, right? So I learned controls in Simulink originally, and so it made a lot of sense to me. And so diving into C code, for instance, can be overwhelming. And so Simulink is great for that. And the support, this BeagleBone Blue support package is really fantastic because it does all that communication to hardware for you. And so ultimately you have just a block that you can see on your screen here that says, output to motor or IMU, and you get the data and it works. And you're not bogged down with dealing with software and hardware necessarily, and so you can really go straight to learning the controls.
I think we were talking about this earlier that you can use things like these for writing test models. So for example, if you want to write to a particular motor, you would just go in there and you can change how the motor behaves, which port you're connecting to. And then if you want to kind of excite this motor in some way, you can change this value live while you're running. You can swap that out with something like a sine wave. And it's just like a pretty quick way to prove things out before you actually start developing the fun stuff in between. So on that note, we're talking about this as being the first stepping point to creating a model that's more elaborate, that actually does something of significance. So what we want to run you through now is an example with this eduMIP robotics kit. So Kurt, and I think you had a few things to say about this kit.
Yeah. So the eduMIP robotics kit is based off the BeagleBone Blue. It's a mobile inverted pendulum. Again, it has the software support library I mentioned earlier, but ultimately we're using the wheel encoders and the IMU for state estimation here. There's low-cost DC motors that control the wheels for balancing control, and all the controls work is model-based, developed in MATLAB, and then implemented in Simulink. And so this is really a great low-cost learning environment for students to touch hardware, learn controls. If they want to get involved in the low-level hardware stuff, like programming, C programming, if they can. But the Simulink environment is really great, sort of graspable environment for typical college student.
So yeah, I think it's time for us to go look at how we did all of that. So this is the Simulink model for the entire self-balancing of the eduMIP that was worked on at UCSD. Kurt and I want to run you through this because there's a lot of fun going on here. One thing you'll notice is, this model is split into the kind of the logic and the monitoring, right? So I think the monitoring is the easy part. You're just blinking an LED to show that things are running, and then we can hit one of the buttons on the hardware to stop it. But the real meat of the model is here on the left, which is, it's a feedback control system. So yeah, I think the balancing is probably where most of the things are. So why don't we dig into here? And I guess this is also where we have your typical feedback control structure, right? You have the controller and the plant.
Yeah, on the right we have our plant block, and we can dive into that in a second. So in the plant we have ultimately what we're measuring on the eduMIP, right? So we have our motor encoders that we see in the bottom. So there's two channel encoders. There's a right wheel and a left wheel, and those get averaged. And so we have some gear ratio that we have to account for. But ultimately, we're getting our wheel location, green in G2, and then in G1, it's the inner loop plant. And we're using the accelerometer there and a complementary filter on the Y and Z accelerometer and the gyro to output an angle of the eduMIP. So the IMU gets this angle of the board, right? And so as you're driving around, this board might be rotating back and forth, and so the IMU is able to measure that, and that gets outputted into the theta and phi, theta there, and then phi is the wheel angle. And so then also in the plant we have our output to the motors that you see on the left in blue. There is our input to the motor value U that gets scaled up to negative to positive 100. There's a polarity for each motor, and then those go out to a right motor channel. So with Simulink, what's really nice is you're using the same function here, but just specifying what motor you are. So if you were to double click on the motor, for instance, block, it tells you everything you need to know about it, and it says, hey, we're using motor 1, and so on the BeagleBone Blue board, there's 4 little motor inputs, and you just make sure you plug in your motor cable into motor 1.
Yeah, and if you want to double check, you can always view the map of the pins, which this is a really handy tool for me because there are a lot of things to plug into on the BeagleBone Blue. And then I guess if we go up, then the other big piece here is the controller here. And we'll get to this enabled piece in a bit, right? But assuming the controller is on, we can dig into it, right?
Yeah, so on the left side, we're getting feedback from, so item 2 there on the left, we're getting our phi, which is the wheel encoder angle, or the wheel angle that we're measuring from the combination of the encoders. And so this is a successive loop closure, or cascaded controller it's often called. So it's a multi-rate controller. So ultimately, our wheel angle goes into the first encoder. There's an integrator there you see that's added on to make sure the MIP doesn't drive off the table. But that gives us a theta reference. And so again, theta is the angle of the MIP of the board itself. And so we're subtracting off the actual what we're measuring for the board angle from the reference angle. And so that gives us sort of an error signal that goes into our inner loop or fast loop controller, if you will. And so these are two discrete time controllers developed in MATLAB in continuous time, actually, and then ported over to discrete time using Tesla's approximation. And so what's nice about this is that if you want to change your controller in MATLAB, you're able to then come here in Simulink and just type in the numbers, change your gains, do more fine-tuning, and actually see the performance on the robot immediately, rather than having to hard code it in C and recompile it and then move it over to the robot and hope you don't drive it off the table.
Exactly. So yeah, these values, I mean, they look very magical. You just mentioned you had some MATLAB scripts, so you think we should dig into these?
So here we have the BeagleMIP model. It's based off an inverted pendulum, but we're putting a wheel on the bottom there. So this is the free body diagram that you see. If you scroll down a little bit, these are the linearized equations of motion. So if we're using a Newton-Euler equations or Euler-Lagrange, you end up with the same dynamics equations here, a second order differential equation. That is linearized here around the set point of the MIP being inverted.
Right.
So these are those equations, and then this script that we've written has all the specifications for the eduMIP, including the gearbox and motor inertia, if you can see there. And so here we have the inner loop dynamics, right? So we have our transfer function G1, which you see there, and so that's in continuous time. And we can look at the Bode plot and the root locus plot shortly. And again, same thing for the outer loop. And so then we can design a controller. We're using lead lag control here instead of something like PID control. And so what's great is we can change where we're putting these poles easily here and rerun it and then get a new transfer function and change it over. So if you scroll down, we'll see figure 1. And so here we have for our inner loop, you have your controller multiplied by your plant, so D1, G1. This is now your open loop, inner loop, and you can see we have a good gain margin, a good phase margin, and on the left we have our root locus. And you'll notice in the Nyquist in the bottom left, we're actually circling the point at -1. So this is actually an unstable system, and that's why we need the outer loop, right? If you do look at the step response in the bottom right, it does look like a stable system. You know, it settles down to that 1, or if you're changing your gains by 20%, it goes a little above or below. But if you take that time out to infinity, it will go unstable. So it's stable in the short time, but ultimately long period time it'll go unstable, and that's seen by circling the point at -1 on the Nyquist plot.
So then with the outer loop put in, then hopefully then that goes away and we ideally get a stable system. So let's take a look at that one. I guess we scroll down and get the other figure, and that's going to be this one.
Okay, so here now we have the open loop system as a whole, but that includes the closed loop inner loop, if you will. So we have our outer loop controller multiplied by the closed loop system multiplied by the outer loop plant. And so there you can see our controllers that we've developed have a really good step response in the bottom right, and in the bottom left in the Nyquist we're no longer circling the point at -1. And you can see also that all our poles are on the left half plane.
So then you said you kind of took this design and then you discretized it, which I guess you have right at the bottom here.
We're using the C2D Tustin's approximation. So we have our continuous time transfer function. We're doing Tustin's approximation, and that gives us a discrete time transfer function. And so we look at those values of D2Z, that should be exactly what's in the Simulink model as well.
Perfect. So I think at this point we want to see this eduMIP in action. All right. So we're going to run this model in what's known as external mode, which means that there's already going to be a connection between the model and the eduMIP. So you see now it's going to start building the code. And when this is all done, this Simulink model, the generated code is going to be on the eduMIP, and there's going to be an interface that lets you communicate with this model. So while this thing starts, I guess one thing we didn't talk about was this startup logic, and I think it's there probably for safety reasons, right?
Yeah, so So if you start the controller without any safety logic, it might just try to drive off the table, or the motors might saturate. Additionally, the IMU takes a couple seconds to sort of settle into its proper orientation, right? So when you start up. Lastly, and I think one of the most important features here that I worked quite a long time on is the soft start counter. And so when all these other flags are not triggered, so we're not saturating the motors, the eduMIP is upright, we've waited long enough to put it upright to start, and you have the eduMIP standing on the table. Once those finally get triggered, it'll just drive away from you, and the interaction with your hand will cause it to fall, and then you won't be balancing. And so the soft start takes care of that, and over about a second, it ramps up the output to the motor from 0 to 100%. So that gives you about a second of time to realize, hey, the motors have kicked on, and I can let go, and then it starts driving on its own. And so it really makes the usability of the eduMIP a lot better.
Right. Interesting. Yeah. So let's see what happens then. I'm just going to pick up the eduMIP here, and I'm hoping that by the time it's in a good position, then that control is going to be enabled at 1. And then if I let it go, then it should start balancing. See, first it started recovering from the little kick I gave it with my hand, but it's going to be balancing. And now that this control is enabled is where we can start looking at some of the results on the scopes that we were talking about, right? So particularly here we have the control effort that's being applied to the motor. So this is that U value, right? That goes to the motors, and then under the control, then I have the scope for phi. This is the wheel, and then theta, angle of the actual pendulum. So what we're saying here is for the eduMIP to stay still, we want that phi to be 0, right? So it's not moving forward or backwards, and then theta is the reference angle that we want to be at, so it doesn't fall over.
Correct. And one of the really cool things here that you may be able to try is to adjust your gains to see if you can get it to balance better, right? So if you bump that gain up to 1 or 1.1,
go 1.1, and then you see that it's responding a little faster, and then we can go look at those plots again, and you can see
how they're acting different.
Right.
But really, looking at the robot tells you whether it's balancing better or not.
So great, Kurt, thank you so much for being on this video. I think we ran through a lot of great things about the eduMIP, about BeagleBone Blue, and how it can connect to Simulink. All I'll say is that at the top right here, you'll see some additional resources for how to learn more about BeagleBone and eduMIP at the UCSD Robotics website. And for us here at MATLAB and Simulink Robotics Arena, you know how to contact us, and hopefully we'll stay in touch. Kurt, thank you so much.
Yeah. Thank you so much. Hope you guys enjoy it. Good luck.